Okay, so now let's look at a current carrying wire, and the current is pointing out of the page. So the circle represents the cylinder that is the wire. The dot represents the direction of the current. So again, stick your thumb out of the page towards you, your right thumb. So my magnetic field line should do what? Circle counterclockwise. Now imagine that I can draw beautiful concentric circles, and they're all counterclockwise. And now these circles are getting weaker and have a weaker magnetic field as I get further from the line, but pretend those are beautiful concentric circles. Okay, so then what is the direction of the magnetic field over here at point P? I like it, Katie. It's up. Pretend like that's tangent to the circle. So your magnetic field will be straight up. What about right above my wire right there? Show me. To the left, to the left. All right, now what about this one? What if I go from my wire over here like a 45 degrees from the vertical to a point right here, point P? Left, right, up, down, down into the, tangent to the circle, right? So I have a question. What is the orientation of a tangent line to the radius of a circle? Perpendicular. So you can look at these being the radius. This is the distance, the R to the wire. And again, that was an ugly B right there, but it should be perpendicular. And this one should be perpendicular. And then this one should be perpendicular. Now what if it's going into the page, away from you? So again, the circle is the cylinder of the wire. The X represents that the current is going into the page. So what does your magnetic field look like? Clockwise, concentric circles, getting weaker and weaker as we get further away. Again, pretending that I can draw concentric circles. Sorry, that's so unpretty. Okay, so now my question. What is the magnetic field over here at point P? Straight up, tangent to the line. That's right. All right, what about down here at the very bottom? To the left, to the left. All right, now what about up here at like the 45 degrees to, and I picked 45 degrees just because it's easy. I mean, it could be any angle. So which way? Down and to the right. Now, if these two wires were near each other and you were looking at a point, I don't know, right up here, P, this wire right here would contribute a magnetic field at point P. Now, is a field a vector or a scalar? Vector, very good. It has, as soon as you start throwing arrows on something, it's totally a vector. Sorry. All right, so what is the direction of the magnetic field due to this left wire? I'm going to call it wire A, and this can be, oh, no. I can't use X or Y or A or B, because what's B? How about this is be wire 1, and this can be wire 2. There we go. Not necessarily, but maybe you have a current that's, maybe this is a wall, and we've got current flowing in 2 different directions for some wires that are in the wall, or something like that. So there are 2 wires near each other, and they have opposite currents. So at point P, what's the direction of the magnetic field due to I1? So imagine that concentric circle passing through point P. So you imagine that concentric circle got to be tangent to that line, up and to the left like that. So I'll call that B1 because that's the magnetic field of that guy right there. And then what about the magnetic field at that same point P due to wire 2? Tangent to the circle, 90 degrees to the radius. So those should be 90 degrees like that. That sort of thing. Oh, so now these guys, oh, do they have X